this conference. Today I would like to talk about the simplest generalization of the null inertial mass density. This is the vacuum energy, absolutely. And we are searching for whether it alleviates the deviations from the null inertial mass density, may alleviate the H0 tension and the tensions actually. I may start with the lambda CDM. Lambda CDM has been amazingly successful in describing the observable universe, and it has some assumption, something like besides the theoretical problems of lambda, we have seen that with the increased accuracy of data, there are different problems appearing about the lambda CDM. It's based on general relativity, so we can say that the Yankee identity is satisfied, and it implies the energy momentum tensor conservation. The energy momentum tensor inside the universe, this is the positive cosmological constant, and the cold dark matter and radiation. This is based on the standard model of particle physics. And we consider the universe, geometry, and topology are as symmetric as possible. We have some problems with the lambda CDM. Actually, we have seen that it becomes, it's very difficult to explain by canonical extensions of lambda CDM. There are many proposals to relax, alleviate the tensions in the literature by changing the late universe, early universe, but we know that we should keep it theta star as the measured value, because this is measured almost independently with a high precision. So what's the way of this? Theta star is the ratio of R star over dmz star, and if you, R star is related with the Prairie combination era, and dmz star is related with the late universe. So if you keep it as the same, you need to check, if you don't touch the early universe, if you are focusing on late universe, dmz star should be kept constant. Another clue about dark energy, this is the Boss collaboration paper. This is the first images of the model-independent way of the getting something about behavior of dark energy. We have seen that there is a negative energy densities at high redshift. The data favors negative energy density at high redshift. Let us think that we should keep dmz star constant, and at high redshift we have get negative contribution from dark energy. It means that this is a mechanism to work it, and we can enhance the HZ at low redshift, as we know, and as well H0. Actually, when you reconstruct the dark energy by considering the interaction between dark energy and dark matter, you can again get the sign change, the negative energy density for the dark energy. This is in the recent paper of Escamilla et al. And let us look where is the inertial mass density. Inertial mass density actually, as Özgür told in the morning session, this is the addition of pressure and energy density. It appears, actually, this is the proportionality constant between the spatial gradient of pressure and the force acceleration. So this is the analog of second laws of Newton, and this is the proportionality constant. But cosmologists can overlook this equation because there is no spatial gradient of pressure, there is no acceleration because there is no force, and so rho plus phi is the proportionality constant. But it is actually the inertial mass density. This is the inertial mass density. Yeah, if we follow the parameterization proposed by Barrow for the graduated inflation, the inertial mass density can be parameterized with this parameterization, as Özgür showed. And gamma 0 corresponds to lambda, now inertial mass density. On the other hand, if you keep it small lambda as 0, it corresponds to a constant inertial mass density. And constant deviation from now inertial mass density can be. What will the data say? We have investigated in the paper Akarsu, Aquaviva, Akarsu, and Vasquez, our paper, and we have seen that, we have searched for what will the data say, and at which scale, if it is not 0, at which scale we should search for it, okay? Of course, there's a possible deviation, dynamical deviation from now inertial mass density, and it may give rise to some non-trivial behaviors, as in the graduated dark energy offered by Akarsu, Barrow, Escamilla, and Vasquez. They work on it, and they realize that there should be a rapid transition to the negative energy density, and it corresponds to phenomenologically there's a sign switch on the lambda, because the date when you look at this plot, there is a lambda CDM, but the negative lambda is favored in this region, and it can be obtained from the graduated dark energy. But it needs a very large negative values of lambda. And this is the actually starting of the lambda CDM model, because lambda CDM model has actually, with a signal function, you are changing the rapid transition from the positive values and the negative values of the same lambda. And this is the very, very promising model in relaxing the tensions. In this talk, I will focus on simplest extensions, lambda CDM extension, simple graduated dark energy. It means that we are keeping the inertial mass density as constant, and we are using the curvature. Curvature actually comes to play because we know that the fact that the Planck data favor positive spatial curvature on top of the lambda CDM model implies such dark energy models, and when we see it, okay, the simplest choice for negative inertial mass density is the spatial closed universe, because it has a negative density parameter. Our main question was to let us look with the constant inertial mass density with a simple graduated dark energy. If it is negative, we can again get a flat lambda CDM model with these types of source, alternative to the null inertial mass density of the cosmological constant. The main question was this, and we know that on the beginning of the road for the lambda CDM, if we can look for separately, it doesn't successfully realize such a scenario because there is a deviation from the W, this is the equation of state, with the actually negative energy, the negative inertial mass density. It deviates much, this is minus 1.3. And when we look at just spatial curvature, we have a 10% of the universe can be attributed to the spatially closed universe. Okay, and so let us look, and can these together successfully realize such a scenario? If the inertial mass density is negative, this is important because it resembles lambda today, but it leads a different feature singularity, dubbed as little sibling of the big grid. first proposed by Bahmudi Lopez et al. To the literature. Because H dot is directly depends on the inertial mass density and it becomes positive, and H dot does not blow up when A and H goes to infinity. Another alternative, if inertial mass density is positive, there will be a feature bounce. Okay? Let us look what the data say. When we do the observational analysis, BAO, supernovae, and cosmic chronometers without plug, as you see here, there are four models, lambda CDM, O lambda CDM, DE, and ODE. We are calling the DE for simple graduated dark energy. And as you see here, contrary to our initial expectations, simple graduated dark energy favor positive inertial mass density. And so this positive value actually worsen the H naught tension. And as you see, this is not favored when we compare with the lambda CDM, and when we consider the simple graduated dark energy with the curvature, this corresponds to 12% of the universe is attributed to specially closed curvature, positive curvature, and this is also is not favored when we compare with using the relative Bayesian evidence. So we obtain a negative correlation between omega k0 and WCI0. When we add blank, as you see here, the full data, joint data set, has shown that the inertial mass density is positive. This is very important because in this 1 sigma results, there is no zero here, okay? And no inertial mass density is favored in this theory if you allow a deviation, constant deviation, not any dynamical deviation. So it means that data favors a positive inertial mass density. And when we look at the relative Bayesian evidence, you can see that it also has the same evidence, okay? You cannot distinguish lambda CDM and simple graduated dark energy model. It means that there's a slight positive inertial mass density. And actually, when you look at the models, the spatial curvature is not favored with the full data. Okay, we have the same evidence for cosmological constant and simple graduated dark energy with an inertial mass density of the order of 10 to the minus 12. As you've seen here, inside the 1 sigma, we have seen that the positive values, this is the dashed black contour, and as we can say that this is on the order of 10 to the 31 gram over centimeter cube. This is the positive inertial mass density of the vacuum energy. This is interesting because maybe not the vacuum energy density, but the vacuum inertial mass density is a constant of nature. Okay, let us look for the asymptotic behavior of the models. As you see here, when we don't use plug data, negative inertial mass density are allowed, and so different LSPR scenario can be seen here with the red one, and blue and black one corresponds to finite bounds. This is the positive values are favored for both cases. But these have different features, okay, rather than the de Sitter feature. And for the full data, we can see that only generic behavior from the simple graduated dark energy models is the recollapsing of the universe in a finite feature, whether the plug data is included or not. Okay, we have been searched for if there's a inertial mass density if we don't consider as zero, okay, we find a positive inertial mass density. And then we ask ourselves, how can we find a way to keep it zero, but some differences? Okay, in the literature, recent literature, there are some suggestions to address H0 tension and other tensions by reanalyzing the cosmological data, breaking down the Robertson-Walker framework. And there are some papers on it, and actually there was very common in the past. There are some models, and they're very popular in some times, and Planck has some clues about anisotropy or something else. But we are looking for how we can keep this zero for inertial mass density. Okay, when we look at the T mu, okay, for the general energy momentum tensor, you can see that pi mu nu is the anisotropic pressure, and it comes to the inertial mass density definition. It enters to the inertial mass density definition with the pi mu nu, okay? And so, if we keep as zero again, we have a particular relation, okay? What will the correspondence of this? We have collaborated with, this work is based on the formed vacuum energy by Akarsu, Özgür, Ancan, and Alberto. This is the generalization of the usual vacuum energy by allowing anisotropic pressure. And we have still in GR with anisotropy, and we have a fluid still has a null inertial mass density. Okay, when we add all the pressure contributions, we obtain, there's a relation between the skewness, because the directional Hubble parameters are different in the BIT type universe, we need to keep one is different, and the skewness parameter and the equation of state parameter. And this T mu does not correspond to the known anisotropic sources such as vector field, topological defects, or something else. And let us see, this is surprising, we haven't actually expected. When we consider these actually particular relation to keep it zero inertial mass density, we have two systems. One is for canonical scalar fields, okay, cosmology. The other one is the anisotropy with the Bianchi and considering there's a Einstein field equation, Bianchi metric, and anisotropically deformed vacuum energy with a particular relation. This is the field equations. Mathematically, they are equivalent to each other under this following transformation. There is a relation between the skewness and the rate of change of the potential, and this actually, the change of scalar field directly determines the cosmic shear, okay, the square of cosmic shear. And so we can reconsider the cosmologies employing a canonical scalar field. We can get the same system, but physically they are different. Actually, these are very similar, and this motivates us when we think about the Klein-Gordon equation and shear propagation equation. Okay, it means that you can construct cosmologically, okay, you can get all the scalar field correspondence with an anisotropic counterpart cosmology. But we have a one bonus, because the kinetic term, potential of the scalar field, they are not measurable. On the other hand, we have a shear, okay? We have a shear and we can measure the shear tensor, okay? From the difference between the Hubble parameters, directional Hubble parameters. This is very important. you can think that you can also the anisotropic cosmologies are very difficult to calculate, and you can calculate by using the scalar field equations, and you can get the information about the anisotropic counterparts. So this is very applicable, and you can easily apply the following these transformation. Okay. And interestingly, in the standard general relativity, we have a shear, okay, cosmic shear. Anisotropy goes with the 1 over a to the 6, 1 over volume squared, and so it spoils the BBM, so it should be very, very small. On the other hand, when you do these relation between inertial mass density and the anisotropic pressure, you can get a term, you can get a dark energy density and shear energy density. It's going together. Shear scalar goes with together with the dark energy, and so it becomes dominant in the late. It becomes slightly affect the current universe, but do not touch the early universe because it goes with 1 over z over 3 times 1 plus w. Okay. Thank you very much. And our question now, can it be derived or predicted from a fundamental theory of physics? And there are some ways to get it, and we have analyzed in a detailed way. Thank you very much.
Thank you.
Very nice. I have a question. This inertial mass tension density can be also a part of the gravitational pseudo-tensor. Because in that case, it could be also related with some affine transformation. That would be interesting.
Gravitational pseudo-tensor?
The part of the stress energy tensor connected with the gravitational field.
This one.
So, indeed. So, the one that is considered the complex, just in the Landau approach.
Ah.
Because in that case, this could be related with the fact that you are interacting between standard matter and gravitational field. And in that case, your mechanism could work, in my opinion, very well.
Okay. Okay, let us see. Yeah, I don't know.
The Landau Lifshitz
yeah.
In that case, I think that it could be connected.
Okay, this one. This
yes,
one.
yes, as you defined it.
Okay, we can divide into gravity and matter.
Yes, yes, yes.
By this way.
Indeed.
Okay, thank you.
Isabella, so your anisotropic stress here is fundamentally related to kinematical effect, which is translated by the shear in anisotropic model. Is that so?
Can you repeat it? I couldn't.
So what I'm saying is, your anisotropic stress here is determined by, it's related to shear, as you say.
Yes.
So it in a way, is related to just to a kinematic effect in the sense that the shear wages how different directions in an anisotropic spread model.
Yeah, it gives contributes the Hubble parameter in a different way.
Yes.
It has 90 degrees and it's like a quadrupolar H, something like that.
So, but in fact, most of the anisotropic models have also intrinsic curvature.
Intrinsic curvature.
Yes. Which is, in a way, translated by the Hard tensor. So, the electric part of the Hard tensor. And it is possible to see that if you have shear-free models in the anisotropic contexts, the pressure is related to the electric part of the particles. So there is a deeper relation yet with curvature than with gravitation between the anisotropic stress. Not just with the shear, but with the intrinsic curvature.
Yeah, but the systems are, okay, under this relation, we get these relation, and okay, this is something like anisotropic source that we don't know. And when we apply to the field equation, we can get them mathematically the same equation. They don't give they are physically very different equation.
What I'm saying is, you're looking for a relation between something which is mathematical and not intrinsic.
Okay, it's about the relation between the inertial mass density and the anisotropic pressure.
Yes, I mean, for instance, you could have a shear-free model.
Yeah.
And still, you would have anisotropic stress, but then it would be a back reaction to the resistance of the body.
Okay.
And that would be okay. Shear-free, so you know from the analysis of shear.
Okay.
I've shown that in 92. It's
Okay.
Okay, thank you for the comments, Nihan.